engineers have to guard against.
And speaking of risks, oxygen compatibility is another huge challenge. The Apollo 1 tragedy is a stark reminder that materials safe in normal conditions can become lethal in an oxygen-rich environment.
Absolutely. Oxygen compatibility testing, like the ambient crusher liquid oxygen mechanical impact test and the promoted ignition test, is essential.
Right.
These tests simulate conditions where an unexpected ignition source could turn routine materials into hazards under high oxygen pressures and temperatures.
It's almost terrifying to consider how something as common as oxygen, if not handled correctly, could lead to such catastrophic accidents.
Exactly. That's why engineers are so meticulous about design, opting for thicker sections, lower pressures, and materials known to be oxygen compatible. Now, switching gears, let's dive into polymers and composites, the real driving force behind the lightweight revolution in aerospace.
Yes, these materials not only reduce weight, but open up entirely new design possibilities. Polymers, especially when combined with reinforcing fibers like carbon and Kevlar, create composites that are strong yet incredibly light, right?
Right on. Polymers themselves can be classified as thermoplastics, thermosets, or elastomers. But the exciting part is how adding fibers transforms these into composite structures that can handle incredible stresses. In composites, the fibers act like a skeletal framework in a polymer matrix, preventing catastrophic crack propagation, even if layers start to delaminate under damage.
And that's a key difference from metals. Composites are designed to handle minor damage without a single catastrophic crack running through the whole structure. It's a different design philosophy suited to both aircraft and launch vehicles.
Exactly. In aircraft, the design accommodates thousands of flight cycles, whereas launch vehicles are built for a single mission. You end up intentionally testing composites with notched specimens, which counterintuitively reduces variability and better reflects real operational flaws. It's all about realistic performance, not just ideal lab conditions.
That's really smart, designing for damage from the get-go instead of assuming perfection. Now, thinking about this whole ecosystem, there's more than just materials. It's the entire process of design, simulation, and real-world testing that makes it all work.
Absolutely. It's a full circle process from engineering design to prototyping, testing with finite element analysis, and then real-world validation. Digital twins, for example, have revolutionized how we simulate manufacturing and manage service life.
Digital twins are like a virtual clone of your aircraft or rocket, huh? It's pretty wild how closely simulation can match reality with the right data.
Right. Tools like FEA software play a huge role in predicting how these materials behave under load. And then vehicle dynamics testing with sophisticated data acquisition systems confirms that the digital models are way off the chart with real-world performance.
Now, if you had to pick one material property that you think might be the next big leap in aerospace performance, what would that be? One that maybe engineers sometimes overlook.
That's a tough one. I'd say the perfect balance between strength and damage tolerance is key. It's not just about having a high-strength material, but one that can still stretch or deform safely when flaws are present. That predictable failure strain, like that consistent 1.5% strain limit, regardless of fiber orientation in composites, gives engineers a reliable design parameter. It's subtle, but absolutely critical for pushing boundaries while keeping safety in check.
I see your point, and I somewhat challenge that though. Wouldn't you say that in some scenarios, focusing too much on damage tolerance might compromise other properties like fatigue life or even weight? There's a trade-off everywhere.
Well, absolutely, and that's where the art of engineering truly comes in. It's a balancing act. You have to prioritize based on the mission, whether it's a long-lived aircraft or a one-time launch. In both cases, optimizing the interplay between strength, damage tolerance, and weight is what really drives innovation forward.
That makes a lot of sense. It's like trying to build the ultimate sports car. Maximum speed without sacrificing reliability. Every little compromise counts.
Exactly, and as technologies evolve and our understanding deepens, we'll see even more innovative materials and processes emerge to push the envelope further. The interplay between traditional metal processing and newer composite fabrication is a testament to ingenuity in aerospace engineering.
This conversation really underscores how cutting-edge aerospace isn't just about raw power, but a symphony of material science, engineering processes, and constant innovation.
Absolutely. From the super alloys that brave extreme temperatures to the composites that redefine lightweight structures, every detail matters. And as we continue to perfect these materials and methods, the sky literally isn't the limit.
It's been a fantastic journey through these complex yet fascinating topics. Thanks for diving deep with me. Every flight really is a marvel of engineering, and understanding the material side gives us a whole new appreciation for it.
Exactly. And thanks for joining in this exploration of how advanced materials shape modern aerospace. Until next time, keep looking up and appreciating the intricate blend of science and art that makes flight possible.